Today we will discuss invariant subspaces of Hilbert spaces. In the last lecture, I have discussed this topic. Today I will continue the topic. First, we have a definition. Let H be a Hilbert space and T be a bounded linear operator on H. A closed subspace M of H is said to reduce T, or T is reduced by M if and only if both M and orthogonal complement of M are invariant under T. That is, T is reduced by M if and only if T image of elements of M is contained in M and T image of orthogonal complement of M is contained in orthogonal complement of M. Now we shall prove a theorem which states that let P be a projection on a closed subspace M of a Hilbert space H and T be a bounded linear operator on H, then M reduces T if and only if Tp is equal to Pt, that is, P commutes with T. Here it is given that P is a projection, that is, P is an orthogonal projection operator on H whose range space is M, which is given as closed subspace of H, and T is a bounded linear operator on H, then we have to prove that M reduces T if and only if Tp is equal to Pt. Let us prove this theorem. We know that M reduces T if and only if both M and orthogonal complement of M are invariant under T. We also know that, actually we have proved this result in the last lecture, that if P is a projection on a closed subspace M of a Hilbert space H and T is a bounded linear operator on H, then M is invariant under T if and only if Tp is equal to Ptp. Now we claim that I minus P, here I is identity operator, so we claim that I minus P is a projection on orthogonal complement of M. As the identity operator is linear and since P is a projection operator, so this is also linear. So I minus P is also a linear operator on H, as we can check for any xy in H and for any scalars alpha beta, I minus P of alpha x plus beta y is equal to I of alpha x plus beta y minus P of alpha x plus beta y. As I is identity operator, so image of alpha x plus beta y under I is the element itself, that is alpha x plus beta y. And since P is a linear operator, so here image is alpha of px plus beta of py. So here we get this. Then we can take common alpha here. We can write alpha of x minus px plus we can take common beta. So we can have beta of y minus py. And this can be written as alpha of I minus p of x plus beta of I minus p of y. So this shows that I minus p is a linear operator. Now I minus p whole square is equal to I minus p is equal to I square minus ip minus pi plus p square. And since I square is equal to I, ip is equal to p, pi is equal to p, so here we have minus 2p. And since p is a projection operator, so p square is equal to p. Here we can write p. So we have I minus p. So this shows that I minus p is an idempotent operator. So it is linear, it is idempotent, and so I minus p is a projection operator. Since we want to show that I minus P is an orthogonal projection operator, so we have to show that I minus P is also self-adjoint, because we know that a projection operator is an orthogonal projection operator if and only if it is self-adjoint. We observe that I minus P is self-adjoint, as I minus P of star is equal to I star minus P star. Since identity operator is self-adjoint, P is an orthogonal projection operator, so this is also self-adjoint. So P star is equal to P, I star is equal to I. So we have I minus P. That is Hilbert adjoint operator of I minus P is I minus P. So we can say that I minus P is self-adjoint. Hence, I minus P is an orthogonal projection operator on H. So we have an orthogonal projection operator, but we want to show that this is a projection on orthogonal complement of M. So we have to find the range space of I minus P. Actually, we have to show that the range space of I minus P is orthogonal complement of M. That is, we have to show that I minus P of X, for X belongs to H, this collection is equal to orthogonal complement of M. For each X belongs to H, we know that X minus Px belongs to the range space of I minus P. We note that P of X minus Px is equal to Px minus P square X. Because P is linear, we can write this. And since P is a projection operator, so P square is equal to P. So here we have Px minus Px, that is equal to 0. So this implies that P image of X minus Px is 0. So this implies that X minus Px belongs to the null space N of P. But we know that M is the range space of P. So orthogonal complement of M is the null space of P. So X minus Px belongs to orthogonal complement of M. That is, I minus P of X belongs to orthogonal complement of M. That is, the range space of I minus P is orthogonal complement of M. Since I minus P is an orthogonal projection operator, its range space is orthogonal complement of M. So I minus P is a projection on orthogonal complement of M of a Hilbert space H. Here, orthogonal complement of M is always a closed subspace. So here I minus P is a projection on a closed subspace orthogonal complement of M of a Hilbert space H. So orthogonal complement of M is invariant under T if and only if T of I minus P is equal to I minus P T into I minus P. Here we are using the earlier result. We have proved that M is invariant under T if and only if Tp is equal to Ptp. So in that case, in the present case, we have projection I minus P. So in this expression, we have to replace P by I minus P. So here we have T of I minus P is equal to I minus P T I minus P. So we can solve this and we can have Pt is equal to Ptp. So we have shown that orthogonal complement of M is invariant under T if and only if Pt is equal to Ptp. And we know that M reduces T if and only if both M An orthogonal complement of M are invariant under T, but M is invariant under T if and only if Tp is equal to Ptp. An orthogonal complement of M is invariant under T if and only if Pt is equal to Ptp. So we have Pt is equal to Ptp is equal to Tp. So we can say that Pt is equal to Tp. So M reduces T if and only if Pt is equal to Tp. Thank you.